Hi everyone, welcome to my channel. This is Leo and let's do some more Leetcode problems today. Today's problem is called LRU Cache. This is a very high frequency problem during an interview. So let's take a look at it. Design a data structure that follows the constraints of LRU Cache. So we have a capacity of the LRU cache that initializes the LRU cache with the positive size. And we have a function called get, so which returns the value of the key if it exists in our LRU cache. If not, we'll return -1. And there's another function called put, and the input is a key and a value. So update the value of the key if the key exists. Otherwise, add the key value pair to the cache. And if the number of keys exceeds the capacity, we can remove the least recently used one from the cache and add the new key value pair to our cache. And there's another restriction. The get and put function should run in O1 time complexity. So let's take a look at example here. So here we have the input like this. The LRU cache gives us a capacity of 2, and we put the first key value pair there. We have 1, 1 in our LRU cache. Let me write it down here. So we have LRU cache of capacity 2, and our first key value pair will be 1, 1, and second key value pair will be 2, 2. So this is the least recently used one. Okay, so let me say if we view this as a queue, at the head is the oldest one, okay, and at the tail is our newest one. So here, and if we get 1, we will return 1 because we have 1 key equals to 1 here, and the value is 1. Okay, so we're returning this value. And second, if we get if we put 3, 3, so at this time we will remove the oldest pair and add the new pair. Okay, so if we get 2, yes, we have a key equals to 2 here, and the value it will be 2. And next we can put 4, 4 here, so we remove the 2, 2, and we put a new 4, 4 here. Now we get 1, so we get 1. Is there anything for 1? No, so we got nothing here. Okay, and we get 3. Yes, we have 3 as the returning value, and we get 4. Yes, it exists in our LRU cache, so we have 4. Okay, yeah, so that's basically a walkthrough of the LRU cache. So how should we implement it? So basically we're designing a storage for key value pairs. Okay, so that functions like a HashMap. But the thing is, we have a capacity restriction. So this reminds us of a queue or list data structure. But there's another problem. It should run in O1 average time complexity. So for queue or list, we have at best ON time complexity. So that's not a consideration here. Is there any other ways that we can think of to implement this? So let's take a closer look here. This is least recently used cache. So basically we really care about the oldest one and the newest one, okay? And everything else can be linked with some kind of data structures, like if something is like this. So if we know the head and we know the tail, we can remove the head in O1 time by just setting the next pointer from 2 to 3. Okay, head.next. was originally pointing to 2, but now we can just point it to 3 to do it in one time. Okay, and for this, adding a new node here will only take 1, so we don't actually care about the things in the middle. Okay, so that makes us think maybe a doubly linked list would work for this. Okay, so, and it should work pretty well, since we have like two-way linked list, basically like this, so that we can reference to the front and the back. Okay, so we can think of a class called list node to implement our LRU cache data structure. Okay, so what should we have here? We should have a key, we should have a value, we should also have a previous, we also have a next. Okay, so that's a doubly linked list node. Okay, oh, sorry about the key here. And let's run the constructor. It should be a key, a value, and this dot key equals to key, this dot value equals to value. Okay, yeah, so that's our basic data structure. But how should we initialize our LRU data structure? We have a capacity. Okay, and like I said, we have a HashMap data structure here, a key value pair. So we also need a map. I think the key is integer, and the value would be a list node, will be its corresponding list node. Okay. Yeah, so I could call it map. Also, I think to be easier accessing our head, our oldest element and the newest element, we need 2 dummy nodes, which is the head and the tail. Okay, so we have a head and a tail. Okay, so for this, this capacity will equal to capacity, and this dot map will equal to a new hash map, and we'll have a node, we'll have a head, will be a new list node. I'll just add some random number in there. Okay, -1, -1, and be sure to connect them together. So head.next equals to tail, tail.previous equals to head. Okay, so that should probably give us the data structure in one time. Okay, let's take a look at the functions here. So for get function, if we don't contain this key in our hash map, we'll just return -1. Okay, so I'll just put it out. So if it doesn't contain key, we'll return -1. Okay. All right. Okay. Yeah. That's it. And if we really contain that key, at this time we get it from somewhere. Let's say if we get 3 from this from this linked list, we have to first remove it from the original linked list and then add it back. Add it back to the newest part of our linked list, because if we get it, we get it from the LRU cache and access it to make it the newest element. Okay, so let's see. So what should we do here? First, we will get the node map.getKey. Okay, we will know where the node is, and we remove it from the linked list, and then add it back to the linked list, and return its value. Okay, so at this time it was fetched from our LRU cache and put to the newest one. So that's basically what get function is about. Okay, so next let's take a look at how we can implement the remove function. So if we want to remove it from the linked list, we can just change the pointers of its previous node and the next node. Okay, so that would be pretty simple. So we have a node.prev. The previous one will be node.next. Oh, sorry, node previous.next will be node.next. Okay, and also node.next.previous will be node.previous. Okay, so pretty simple. We're just changing the pointers here. So let's write something here. So if we have like 3, 4, and maybe 0. Okay, so if we're going to get 4, node.previous.next, so we are connecting 3 to 0, and node.next.previous, we're connecting 0 to 3. By doing that, we effectively removed the 4. Okay, so that should work. Next, let's take a look at the add function. To add a node to our tail, we just have to know if we want to add something between 3 and tail, we have to know the previous node and we have to know the tail. Okay, so let's see. So previous end will equal to tail.prev. Okay, so the previous one with the tail, and we are going to add the new node to our linked list. So prev end.next equals to node, and node.previous will equal to prev end. Also node.next will equal to tail, and tail.previous will equal to node. Okay, so that adds our node to the tail of our linked list. Okay, next we can try put. Okay, so for put, if it exists in our HashMap, we have to substitute the old node with the new one. All right, so list node old node will equal to map.getKey, and we're going to remove it. After removing the old node, we can add the new node for the key. Okay, so we're going to construct a new node, list node, the key is here, the value is here, and we're going to put the key value pair into our HashMap. Okay, oh, not node, this node. Okay, and we're going to add it to our linked list, to our LRU cache. Okay, and there's another restriction here. Don't forget about that. That is the capacity. If it exceeds the capacity of the LRU cache, we're going to evict it from the head. Okay, so if map.size is larger than capacity, we will have a list node to be removed will equal to head.next. Okay, that is the first element after the head. Okay, and after that we're going to remove to be removed, and we're also going to delete it from our HashMap. Okay, so map.remove to be delete to be removed dot key. Okay, so after doing this, we removed it from the linked list, also the hash map, so it's not accessible anywhere. That means we effectively remove the head of the original linked list, and our capacity is fine here. Okay, let's take a look. Oh, okay, perfect. I think it accepted. So for complexity, since we're doing a doubly linked list, so average the complexity is 1 constant. Okay, perfect. It passes all the test cases. Thank you so much for watching. If you like the video, please like and subscribe to my channel. I'll see you in our next video.